Matrices are a cornerstone of modern computer graphics, and even though they are just a bunch of numbers grouped together, they might seem a bit intimidating at first. Maybe you have already tried fooling around a bit at first and were like, yes, makes total sense, and then it ended like, hell, what is this? Matrices are like tables on steroids. They have a dimension which indicates the number of rows and columns, but keep in mind that the amount of rows is mentioned first. Matrices are indispensable for digital object representation because they can essentially represent an object's transformation in space. Therefore, they are often referred to as transformation matrices. A bit more off topic, but an example I absolutely want to bring in order to show how black magic matrices truly are. Imagine an undirected graph and its adjacency matrix. An adjacency matrix is used to show which nodes are reachable by other nodes. An entry in the row A and column B means that there is a way of length 1 from A to B. Since we are in an undirected graph, there obviously also is a way from B to A. And this applies to all connections, therefore we have a symmetric matrix. Now, the real magic happens when we take this matrix to the power of n. So far we have a matrix to the power of 1, so the matrix itself. If we take the matrix to the power of 2, our entries say how many paths of length 2 exist between two nodes. This is a general rule, so if we take the matrix to the power of 3, then we get the amount of paths of length 3 between two nodes. Let's take B to C for example. The matrix says there exist 4 paths of length 3 from B to C, which are BA-BC, BC-BC, BC-DC, and BC-EC. No matter what you do, you won't find an additional path. There doesn't exist a single path of length 3 from C to A, because you could reach A, but then you would only have a path of length 2 and you still need to move one more time. Since this was a little off topic in regards to graphics, let's start out properly this time with matrix multiplication. You can multiply two matrices if the column count of the left matrix equals the row count of the right matrix, which by the way also means that you cannot just swap them, so the matrix multiplication is not commutative. The result of a matrix multiplication is another matrix which has the same row count as the left matrix and the same column count as the right matrix. This is just something you will get used to once I show you how matrix multiplications are actually performed, because a field in the result matrix is respectively the sum over the product of the row to the left matrix and the column of the right matrix. So in our case we multiply the first entries 2 times 2 and add them to the product of the second entries 3 times 3. So the result for our current field is 13. For those who are interested, this would be the result of our matrix multiplication. I will show a complete example later, but now we will need to talk about trigonometry. This is a unit circle. It has a radius of 1. If you draw the radius at any angle and project its end down or up onto the horizontal axis, the length of the center up to the projection point is of the same length as the cosine of your angle. If you project it onto the vertical axis, the length between the center and the projection point is equal to the sine of your angle. You might be wondering what this has to do with matrices, and I will show you soon. But now we make up 3 points in our 2-dimensional plane: 2, 1, -1, 3, and -2, -2. Those points could for example be interpreted as the vertices of a shape, like this triangle in our case. Now we want to be able to work with this triangle. We want to make it do things for us. The simplest thing you can do to a shape is to move it. Sun Tzu probably. For this, you could just add the same vector to all your points. Scaling works pretty much the same. Instead of adding a vector, we multiply all points by the same scalar and we receive a new scaled shape. This is one of the operations which always pivot around the origin of the coordinate system, so 0, 0. You can compare this to the origin property of meshes in Blender. If I set the origin to 5, 0, then scaling will make the object seem as if it was moving away from the origin. Same principle applies if I set -2, -2 as the origin. Rotating is more of a complex operation compared to the previous two, so to keep it simple I will just restrain myself to a single point. Again, rotations need a point around which they rotate. This is again our point 0, 0. I make up an angle of 60 degrees, which if applied to our point would give us this result. But how do you calculate something like this? Let's start simple. How can we use the angle to transform our x-coordinate of 2 to 0.13? Only by using our angle. If we think back to our unit circle, we remember that the cosine could possibly be appropriate to be used for transforming our x-coordinate. So let's try that out. We multiply our x-coordinate with the cosine of 60 degrees, which is 0.5 by the way, which results in 1, so this can't be correct, or at least there is something missing. It would lead us to the correct result though if our original point was laying on the y-axis, so what we need to do is to also account for the offset away from the y-axis. So in order to account for this offset, we subtract our y-coordinate multiplied with the sine of 60 degrees, which is around 0.866. If we calculate the result, we actually reach our desired 0.13, so as it turns out, this seems to be the formula for calculating the new x-coordinate when rotating a point. To hopefully make this a bit more visually appealing, because I don't understand any of this anyways, I will demonstrate this formula in our unit circle. Since we are in the unit circle, we have the radius 1 and we start at 1, 0. Because of y being 0, we just receive the cosine of our 45-degree angle, which per definition becomes the new x-coordinate of our newly rotated 2 position. We fill in the angle, and if we calculate this, we receive 0.71 as our new x-coordinate. If I wanted to now rotate this point by an additional 90 degrees, I insert my x and y coordinate into the formula and I insert the angle into the formula. Let's do one more example where I rotate by an additional 60 degrees. I insert both coordinates into the formula, I insert the angle into the formula, and again we receive the x-coordinate of our new point. If you don't understand this, don't worry, I don't understand this either. And this is by the way the formula for the new y position. It is essentially the same really. But now let me show you something. Let's take this matrix right here and let's multiply it with a point. If we remind ourselves of how matrix multiplication works, we get the following 2 by 1 matrix. First entry of the left row times the first entry of the right column, plus second entry of the left row times second entry of the right column. Now tell me, does this look familiar? Does this look familiar, Shifu? If you compare the x and y values to the formula for rotating points, then you realize that this matrix is essentially doing exactly that for us. So let's go back to our triangle example. In order to abide by matrix multiplication rules, we have to transpose the way we write our xy coordinates, so now they are 2 by 1 matrices. Let's take an arbitrary angle of 30 degrees. If we take the rotation matrix and insert this angle into it, we receive a new matrix with concrete numbers which we can multiply onto our points. Multiplying our triangle with this matrix transformed it into a new triangle, rotated by a certain angle. This matrix template is therefore called a rotation matrix. Similarly, there also exists a scaling matrix, which generally looks like this. If we multiply the scaling matrix onto a point, we receive a newly scaled point. Here is an example to demonstrate this effect. Similarly to how I previously mentioned a pivot point, we also have to take into account where the object is located, otherwise we may risk moving it away from the origin. There is a simple solution to this problem, which is called moving the shape to the center, scaling and moving it back. So let's quickly recap. We know about the rotation matrix, we know about the scaling matrix. There surely has to be a matrix which can move points, right? Well, no, at least not with those dimensions, but there is a trick that can be used that is called homogenization. That means we take a point in our 2D plane and add an additional coordinate to it, which has no impact on where the point is displayed. This is called a homogeneous coordinate. I will color them accordingly, at least for this one example. Now, this makes points incompatible with our previous matrices, so we need to change them too. This is done by also extending them by their own homogeneous coordinates. To demonstrate that the scaling matrix still works, I will demonstrate the following calculation. Obviously, scaling matrices were not the reason we invented homogeneous coordinates. We want a translation matrix. This is how it looks, by the way. X and Y are the vector by which the point is offset. Here is a quick demonstration. If we think back to our rotation matrix example, so far we had to multiply the matrix with what seemed to be each individual point. But nothing is stopping us from just putting all our points into a matrix as well. If we want to scale our triangle by 2 along the x and 3 along the y axis, this will look as follows. It is also possible to chain multiple matrices. Those matrices are scaling by a factor of 2 along the x-axis, rotating by 90 degrees and rotating by 180 degrees. How will this calculation transform our triangle, you may ask? It will be the equivalent of scaling by a factor 2 along the x-axis, rotating by 90 degrees and rotating by 180 degrees, which will bring us the following matrix. As previously mentioned, matrices are not commutative, so swapping two matrices will lead to a different result. What you are allowed to do though is changing the order in which pairs are calculated. This order is equivalent to this one and the same as that. The order you see right now also implies that you can essentially combine different combinations into one matrix, so applying all the operations we did before is essentially the equivalent of multiplying our triangle with this compound matrix. Now I want to talk about a different way for representing objects. So far we know we can put all vertices into a matrix, but there are additional tricks, especially when working with images, since their resolution is already a fixed constant. Therefore there is no need of storing all vertices of an image. All you need actually is a position and a way to represent rotation and scale. The Transform2D class in the Godot game engine does exactly that. Transforms can completely represent an object's orientation, and the Transform2D does that by storing the position of the object as a vector and, even though slightly more complex, scale and rotation with the help of two other vectors. To show you how you can use two vectors for storing scale and rotation, I will exchange the Godot icon with its more or less outline. Also, I move it away from the center just because I can. The origin for this object is 300, 200. Also, it has the two previously mentioned vectors, 1, 0 and 0, 1, which represents the scale of the object. I think it is best if I just show you what they do, because it is easier to see than to hear the explanation. If we move one of those vectors along its local axis, we are essentially just scaling the object. And keep in mind that this applies equally to the opposite side as well. Also, the lines which are parallel to this vector will always be parallel, even if I do this. Both vectors work in the absolutely same manner. Now, you might already see how we can represent rotations with those vectors. I will create a new undeformed square for this demonstration though. If we apply the previously mentioned trigonometry tag, we can do something as follows. The way this works in 3D is, by the way, the absolutely same. For 3D, we just have 3 instead of 2 points to represent our object scale along the axis, which, by the way, obviously have a XYZ coordinate since we are now in 3D. The scaling point for our x coordinate lies 1 unit into x direction, 0 into y and 0 into z per default. Since the behavior is the absolute same as in 2D, I can just move this point along the x-axis in order to scale my object along the x-axis, or move the other point along the z-axis to scale along the z-axis. It gets more interesting though if I offset the point for scaling along the x-axis into y or z direction. Let's imagine an offset along the y-axis. If we expect the exactly same to happen as in 2D, then we would be 100% correct. Offsetting the C point along the x-axis has the absolute same effect.